when teaching complicated physics to A-level students, it's best to build them up slowly if you're going to do Stefan-Boltzmann's law and Wein's law and black body radiation and black bodies. It's best to start them somewhere where they're comfortable and slowly build them up. We'll get to the laws and the formulas and how to use them later on in the videos. But we start the lesson with my polo shirt is black. So what happens to any green light or red light or blue light that come and hit my black polo shirt? Well, they've got energy because of the ripples in the electrical field. When you have electricity, the electric force comes out of the wires and affects things near it. Electrical field. Now, a magnetic field is easier to understand. Magnetism goes distances. When you have a magnet, it will affect other magnets some distance away. And that's called magnetic force field. And this is one of the times where science and science fictions come together to use the same words. Just like with Star Wars, feel the force. Well, the magnetic force and the electrical force. And so light is going across from the sun to my polo neck black shirt as little ripples, like waves on a sea, little ripples of magnetism. So you can see that as like the North Pole of a magnet going in and out, in and out, in and out, making little ripples of magnetism. And a magnetic ripple, we found out, as it collapses, will make an electrical ripple, which makes, as it collapses, a magnetic ripple, which, as it collapses, makes an electrical ripple. This is how light gets across the vacuum of space from the sun to hit light energy from the sun hits this black. What happens to that energy? Well, hopefully the students will remember that energy doesn't get created or destroyed. What's that called? And I'll write it on the board. If someone puts their hands up and says, conservation of energy. Excellent. This is how I teach it to my students in class and my students on Jamboard and Google Meet when I do my internet tutoring in the evenings. And so, when the light energy hits black, what does it become? What sort of energy? Is it going to become kinetic energy and push me across the room? No! Is it going to become electrical energy and give me electric shock? No! Hands up. And so I'll give lots of examples of energies that aren't the one that we're after. And hopefully the student put their hands up and say, what about thermal energy? Oh yes, heat energy. So if they say heat, I'll say thermal. If they say thermal, I'll say heat. Yeah, heat energy. It gets hotter. That's why if you are walking around in the middle of the day, in the sunshine, black is the worst color to wear. Black shoes, bad idea. But if you're in the shade, black is the right color to wear. And this is where I get towards black bodies. People in deserts wear black. Black, loose cotton or wool clothing, but it's black. And the reason why is because black emits really well. It absorbs the energy and it emits the energy. Now, when Newton got a prism, a sort of 3D triangle of glass, and had light coming in, he split the light into all of its colours. So what are the colours that you get? And then hopefully some students will put up their hands and say red, green and blue, because they've already been mentioned by me this lesson already. That's just, these are the three that I've mentioned. Any more colours in the rainbow? And someone might say pink, and then I have to say, oh, unfortunately, pink, no, because pink is red mixed with white, and that's how you get pink. And so pink isn't in the rainbow. And then I'll give them the aid memoir, the way to remember it. So the old way was Richard of York gave battle in vain. Or the new way is Roy, Richard of York. G, so it's Roy. Graham is his middle name, but he calls himself Roy G. Biv, battle in vain. Roy is red. The O for Roy is orange. The Y for Roy is yellow. G, Roy G. Biv. G is for green and blue, indigo, violet. You look at the rainbow in the sky and you're thinking, hold on a minute, it's made by light bouncing off little droplets of water. That's what happens just after it rains. Billions of little droplets of water, and the light coming to you in that rainbow bow shaped with all the colours split apart only hits your eyes. The person standing next to you is getting different light going in their eyes. And if you're in an aeroplane, you see it as a circle, which is just wonderful. Must do that sometime. But those colours, when projected onto a white wall, you've noticed that if you put his fingers next to the red, in the dark stuff, beyond the rainbow, beyond red, he felt warmth on his fingers. And this is why we call it infrared. And equally, if you put your finger just beyond the blue, indigo, and violet, where it's dark, there's a type of light, a type of electromagnetic energy coming from the sun that heats your finger up beyond blue, beyond indigo. But it's ultraviolet, beyond violet. Bees use beyond violet to find flowers. Flowers are lots of different colours, red and orange and purple even. But flowers aren't there to attract you, because humans go up to flowers, grab them, cut them off, put them into a vase. This is the sexual organs of the plant. This is not helping the plant out. So no, flowers aren't for us. Flowers are attracting bees. And bees have the ability to see in the ultraviolet. And so all flowers are bright in ultraviolet. It just so happens that there are also the colours red and orange and blue, and that makes people go and cut them up. Bees can see ultraviolet light. We can't. We've mostly got 3 cones in our eyes, one to detect red, one to detect green, and one to detect blue. What colour do you get if you get equal amounts of red, green, and blue? If my students aren't sure, if they don't put their hands up and give the right answer for that one straight away, I'll say, look at an old-fashioned television. One with big dots. The ones we've got nowadays have got small dots, but the old-fashioned televisions had big dots, and there'd be a red and a green and a blue. The reason why they use those 3 is because when you get equal amounts of red, green, and blue, you get white light. And so with just those 3 dots, you can make all the colours that you needed for a television program. And it still works today. little red dots, little blue dots, little green dots, giving you the light. When they're all equal, you get white. When they're all turned off, you get black. And different amounts of different of them give you all the different oranges and other colours, including pink. Ultraviolet is detected by bees. We'll write that on the board. Infrared is detected by, well, there's an animal that goes down burrows, rat burrows, going there to eat the rats. Now, when there's a fork, there's a left and there's a right. They don't want to go the wrong way. They could use their forked tongues but that smell, or that the horses do, and these animals do, to smell, they get the molecules on their tongue and they put it to the top of their roof of their mouth. And that helps them smell much better. They don't use that method because the smell of rat is everywhere. No, they want to detect the heat coming off them. The infrared, just like an infrared camera that they use to protect army bases and banks late at night. Infrared cameras, they have little pits underneath their eyes. What animal is this? Hopefully I'll get a student say, what about snakes? Oh yes, it's snakes. That's a mark for them. I'm going to write it down in my teacher's book so that when I get to making reports about people, I can go, this person is always involved, always giving good answers. It's in my mark book. Or when I'm teaching and talking to parents in parents' evening, I can show them my mark book. Look, he's got a mark every lesson where he put his hand up and politely gave a good answer. Infrared is detected by snakes. At this point, I start writing on the board all of the electromagnetic spectrum. And now, I'm going to pause the video and get my Jamboard open so we can see those. Once I've said things to my students, I start putting them on the board. And my polo is black. What colours does it absorb? And then the students will put their hands up and say, oh, it absorbs green and red and blue. And I'll say, right, we're going to write those down in an order. Which one goes in the middle? And hopefully they'll know their rainbow that green goes in the middle of the rainbow. And I'm now going to make sure, woo, hold on, come on Jamboard, green, we're going to put that right in the middle. So, black absorbs green, and black absorbs red, and black absorbs blue. Now I've put them in this order on my board with lots of space for a reason, and I'll just let them think about what that reason is. Now, if it's something that absorbs all of the spectrum of different, well, not just colours, but all the different words that make up what comes off of the sun, then if it absorbs 100%, it's called a black body. Now, we do this in physics, even though nothing's purely a black body. Most things do a little bit of reflection of some kind of radiation. We're going to call it a black body because it makes the maths easier. It makes the physics easier. And there are many things like the sun that are over 90% black bodies. My black polo will probably absorb 90, maybe 95% of radiation. We call it a black body. If it does 100, everything is an approximation to a black body. It keeps the maths and the equations simple. Black body absorbs 100%, absorbs 100% of radiation, turning it into thermal radiation, heat radiation. Of radiation, turning it, making heat. turning it into heat energy. We mustn't say making, because that's the conservation of energy. Turning radiation energy, turning it into heat energy. Okay, and as I'm writing this on the board, my students are writing it down because they know there will be questions later and there will be no time to write down what's on the board later on in the lesson. They've got to write it down as they go, and the same for my tutorial students at the weekend. So I'm going to get this line to go down a little bit, something I can't do with a whiteboard. Excellent, so that's what a black body is. We've already got one of the things sorted out for exams. Now, the next thing we need to know is, what is radiation from the sun caused by? Is it little bullets? Well, people used to think it was tiny little things coming over from the sun hitting the earth. And then scientists got a bit more clever and they thought it's ripples. Light, all radiation, radiation. Now, when I say all radiation, all energy radiation, because there are actually particles as well. So I'm going to go energy. Radiation is, now it's ripples. And at this point, I'm going to say, what was the ripples caused by? And hopefully one of my students is going to remember, it's magnets. Ripples in magnet. Now, magnetic and. Now, there was also another chapter in physics which had to be joined to the magnetic chapter because we realized one caused the other, and it's electrical. Now, both of those have effects over a distance, and they don't have to be touching the thing they're affecting. Magnets don't have to be touching another magnet in order to push it away or attract it. And that's called a field when it goes through space and does its job without having to touch it. All energy radiation is ripples in magnetic and electrical fields. And we put the two words together. And we now call it EM radiation. Or we put electrical and magnetic together. Electromagnetic. Well, now, when we've got lots and lots of different electromagnetic waves, it's called an electromagnetic spectrum. And yes, you can be on lots of different spectrums due to your brain. And a spectrum just means that you're more or less like something. Now, the next thing I do is I ask my students, what's the dangerous rays they know about? Now, most of them will go, how about X-rays, because they're dangerous. And I then put in, why does the X-ray technologist, X-ray technician, why do they leave the room? They say to you, it's perfectly safe, and then they go. Why do they do that? And for boys, they put a piece of cloth with some lead in it on your lap if they're going to do the top of your head or your stomach. Why do they do these things? Now, this confuses people and they start getting worried about X-rays. And no, it is safe for you because you've got white blood cells. Your white blood cells go around your body collecting up any bad bacteria or cancerous cells. If you get one X-ray every day, or one X-ray every 3 days, you'll be fine. Your white blood cells will go around going, oh, you're cancer, I'm eating you. But if you're an X-ray technician, you might get 40 X-rays in a day, and that was too many, and the white blood cells can't get them all, and especially if they're smoking. And so we had a whole bunch of people die. All the X-ray technicians all died, and now we've changed the rules. They have to leave the room. So they don't get a blast of X-rays 50 times a day. And they put the lead over your groin so that you don't have mutants. Yes, the sun's radiation comes down, hits your cells when they're dividing to make sperm cells and egg cells. They hit the DNA and change the DNA. And that's how you get, well, 3,000 years ago, ginger people happened. People with ginger hair was a mutation from the sun hitting a gene, and suddenly you've got people with ginger hair, and the Vikings loved them so much that they bred with this one or two ginger people and spread them across the world to Scotland and Ireland particularly. X-rays are dangerous. What other dangerous rays are there? What ones can you get cancer from? So then they might say, oh, ultraviolet, you've said that one already. And I say, yep, what animals can see ultraviolet? And hopefully someone remembers it's bees. Everything I say, I try to get my students to come back with. Okay, any more dangerous ones? Now, the ones that have done GCSEs might remember the ray coming out of atoms when they split apart. There's alpha and beta, which are particles, and gamma, which is the ray. And there's also my favourite one, cosmic radiation. Now, it's called that because it came from the cosmos. We didn't really know what was causing it. And now we know it's part of the solar wind. Have I got them all? I think I've got all the dangerous ones. And then I say to my students, what about safe radiation? Radiation that can't give you cancer. I've already mentioned one. It's cameras, it's heat radiation, infrared. So I like my students because there's infrared cameras, and these the Americans used during the Gulf Wars because their tanks had infrared cameras and the Russian tanks didn't, and that's why it was such a turkey shoot when it came to American tanks versus Russian tanks. The Americans could see them at night because they gave off heat radiation, infrared. The Russians didn't know which way to shoot. The people in Russian tanks didn't know which way to shoot. It was Iraqis at the time. Infrared, I missed that. Infrared, yes. And then, oh yes, that's a mistake I meant to do. Now, what other safe ones are there? And so students might start thinking, oh, well, there's also rays going through your body, and I'm going to get microwaves from somebody. Yes, and then I ask, well, where are microwaves in your daily life? Well, microwaves come out of your phone. And if you put 30 phones around one popcorn that's unpopped, a popcorn kernel, then, and you phone all those phones at the same time, the popcorn gets enough heat to pop. And that meant that when mobile phones were first invented using microwaves, people thought their brains were going to cook. And, well, yes, your brain does heat up when you use your phone, but it's by about 1,000th of a degree C. You need about 30, unless your brains are the size of a piece of popcorn. That always causes a laugh. Someone always gets accused of that one. Then you'll be fine even if you've got 30 phones going on. Right, what other rays? And everybody goes for radio waves, which is amazing to me because they don't have radios much anymore in their cars sometimes. But there's television waves. Now these are 1 mile to 10 miles long. That's why they go around mountains, and everyone forgets the one that's most important to them, which is Wi-Fi. Wi-Fi is kind of squished in here because it uses some radio waves and some microwave bandwidth. I think I've got them all now. I'll add on more if I think of any more. Okay, so that's my electromagnetic spectrum. Cool. And we've got which ones cause cancer all the way to ultraviolet. That's why we wear hats in Australia. In the schools in Australia, they have to wear hats because there's a hole in the ozone layer caused by humans using a chemical for spray cans. The law was changed. The Montreal Protocol, all the governments got together and said, right, we're going to stop using this chemical, and that's healed the hole in the ozone layer and also cut down some of the worst climate change chemicals. We've just got to do the same. All the governments get involved with climate change. We're trying to do that. Okay, these are waves. And with waves, we need to know what V means. And V in waves equals, well, I'll ask my students, what does V mean? And while you're thinking about it, what does F mean? Little f, in waves. And also, what does this mean and how are they all connected? Ooh. Okay, very few people at this stage in their A levels, or seeing as this is going over GCSE, apart from the word black body, this is heading now towards A-level stuff, and they might remember from their GCSE that V equals F lambda. And then they're going to go, oh, V is velocity, isn't it? F is frequency, and then they'll struggle to remember lambda, and I'll often have to tell them it's wavelength. Okay, and you know, it's a Greek letter, it's a word, it's a remember, you'll get it eventually. Lambda is wavelength. That's frequency. Now, I've done this to give them a clue to their answer to the next part. And the next part is, what's the difference between cosmic rays and TV rays that make one dangerous and the other one velocity? The other one's safe. And also, which one of these three things do they all have the same? They're all the speed of light. They all go at the speed of light, so they all have the same velocity. EM radiation has the same velocity equals speed of light. And we've not made anything go faster than the speed of light. Our theories are saying that we'll never get anything go faster than the speed of light. If you do get something going faster than the speed of light, we will become so famous because we've just broke Einstein's stuff. Okay. Now, I did say that these things were coming from the sun towards us, and they're coming as waves, electromagnetic waves, and some students might have got some knowledge and they go, oh, but isn't there a wave-particle duality? And I'll say, yes, there is. That's brilliant, and I'm not going to write it on the board, but save that, we're going to do that in future lessons. The wave-particle duality, but we don't need it now, it's just, there's a lot to do today. Okay, so what has cosmic rays got more of than TV rays? And, well, seeing as velocity is already done, it's got to be the one or the other of them. And so they might get it wrong, they might choose it right, but TV and radio waves are 1 mile long. I've already said that. Whereas cosmic radiation is less than a nanometer. And I can't draw that very well on this thing, and it just gets longer and longer and longer. Okay, and so there's my diagram. That's the difference between the waves. They're all just jiggles in the electricity and magnetic field, and it's a little bit like if I have a pin and I hit you with a pin once every year, you'll get over it, you'll survive. Whereas if I hit you with a pin 1 billion times a second, you'll bleed to death. And that's the reason why cosmic radiation is dangerous and TV and radiation is safer. Safe. You can get it going through your body all the time, it never causes you any harm. And it's kind of like that, that's the way to remember it. That's the way I teach it, that's the way to remember it. So, my next thing to do is, if I've got a cooker and I turn the heat on, if I turn the heat on, what temperature, what colour does it go? It goes red. And so red hot, And then if they've done the light bulb experiments, red hot, what colour, if you put more voltage into a light bulb, what colour does it go? It goes the colour that you get out of filament light bulbs, the ones that have got wires in them. They go white hot. And so which one's hotter? White hot is much hotter than red hot. And so the next part of the syllabus, heading towards Wein's law and that fabulous diagram, we have to explain why red hot and why white hot. And so here we go. Right, okay, so I'm going to press that one, and I'm going to have... Right, so I start off by not saying anything that's difficult to do. Okay, I start off by just drawing an X and Y axis. And I go, okay, and I'm going to put red here. Okay, so that's when you get red, hot. And of course over here I've got blue and green. So there is such a thing as green hot and blue hot, but you don't see it, and I'm just going to show you why. Okay, so if something's about 1,000 to 1,500 Kelvin, it's red hot. So I'm going to put a cross there. Whereas if something's about 2,000, 2,500 Kelvin, it's going to be all three colours. So I'm going to put it going like this. So it's got about the same amount of red and blue and green, whereas this one doesn't have any green. It's got mostly red. Oh, that was difficult to draw. Okay, and this one goes down here, never crossing it. And it comes down here, like this. And so what am I going to call the top of my graph here? The colour it gives the most of. And they might say, well, top, sir, but eventually, hopefully, I'll get somebody, if I lead them, I'll get maximum. Okay. And seeing as this is wavelength, I'm going to use the symbol for wavelength lambda. And this is lambda max, and this comes into formulas. There's a lovely formula that has lambda max, a way of calculating it. And so this is the lambda max of a lower temperature. So if you know the temperature in Kelvin, oh yes, Kelvin, I have to check Kelvin now. How do I convert from degree C to Kelvin? And most of my students get it the wrong way round. So hold on, this has got to be, yeah, about 2,000, maybe 2,500 Kelvin. Okay. I also like discussing the fact that at this point, capital K, that capital K often means thousands, and capital K also means Kelvin, and so you wouldn't put 2.5 kk for 1,000 kelvins. That would really mess up with everyone's head. That's about 1,500 Kelvin, which tells you that if it's red hot, don't touch it. It's hot, okay? Your cooker, don't go and touch it. I've got an exclamation mark there. Okay, let's get rid of that. Got it. Okay, so next, this is your red and your Wi-Fi and your radio waves down here. Let's put Wi-Fi in to make my students happier. Infrared IR radiation is infrared, and Wi-Fi microwaves. Microwaves, because of the size of them, they're micrometer sized. No, they're centimeter sized. Forget what I just said there. Wi-Fi, because they're getting bigger. Okay, there can be a capital F, can be a small f. Originally it was a capital F. Lots of people do it small f now, so whatever. So, degrees C to temperature. So, the way to remember it about Kelvin, when you've got 0 Kelvin, which is fantastic, it's okay. At okay, atoms stop vibrating. The air around you will slow down so much that the gas will become a liquid, the liquid become a solid, and the solid atoms, everything solid. The last thing to make solid is hydrogen, because it's it really doesn't want to be a solid. So you've got minus 200 degrees C and more, everything stops moving. And you can't get slower than stops moving. You can't get less than 0 speed. And so this is another one of those things that you can't get less than 0 K. And so that's why we call it 0. Okay, and at 0 K, some of my students will remember the number 273.16 equals centigrade equals 0 K. And so I always write that down whenever you're doing anything to do towards Kelvin. Otherwise, people do the weirdest things. They add 273 rather than taking it away. So that's a good one to write down. So my students, in my tutorial students and my students in school are furiously writing all this one down. Now we're going to give you Wien's law, because Wien found that the maximum, the colour basically, the colour of the radiation coming off something is related to its temperature. So the hotter it is, hotter, the smaller the wavelength. And that's why temperature is on the bottom of Wien's law. Big number on the bottom, divide by a big number gives you a small number for lambda max. And B is just a number. They will give you this in... That's the displacement constant of Wien's law. They'll give you that in the exams. So you don't need to remember Wien's law. They'll probably give you that. It's only got 3 things, but they'll probably give you that. Best to remember it. But it means that high temperature has got low lambda max. Temp gives... So this is what's coming out of a black body. A black body absorbs everything, but it's it's being radiated. Higher temperatures, you get more and more dangerous radiation. Low wavelength radiation. Rad. Oh no, don't give me this rad. Now, also this is a good time to go through what does radiation mean. And people will say all sorts of things. What radiation means is energy going in every direction. If someone's running around going, help, help, everybody run, and there's some radiation, I want to know, is it sound radiation? Because, sound comes out of my voice and goes to every part of this room. It radiates to every part of this room. Is it light radiation or is it gamma and cosmic radiation? In fact, if it's one of those two, I'm running around screaming as well. So what radiation you've got? Radiation just means how it moves. Let's go to Stefan-Boltzmann. Oh, has everybody written that down? Yes, good. Okay, let's go to Stefan-Boltzmann. Now, Stefan-Boltzmann also had stuff on that. And Stefan-Boltzmann, 2 German gentlemen, I think they sort of collaborated. The per unit area means if it's big like the sun, it'll be giving out lots of energy. Whereas if it's small like my pen, it will be giving out less energy. The sigma is a Stefan-Boltzmann constant. It's just a number, and that's temperature. It's capital T, temperature in Kelvin. Excellent. And now you've got all that, your introduction. Oh, I ought to also say, sometimes this equation is written two different ways. So it can be written as J star so this is just a different way of writing it. Equals sigma a t to the 4. Okay, yes. You do also get it written as L equals. All three of these are possible. You have to check to see which one of those is used. In this case, it's sigma a t to the 4. If it's got an L, it's just in energy per second, because the A is in there. Cool. A obviously is area. And bigger things, A is area. Bigger things give out more energy. And at this point, what we do is we go through questions that are causing trouble from past exams or my online students. We go through the questions that are causing trouble from school. Good. Now that's the basics. I hope everyone's got all that written down at home, because that's the end. Bye!